All right. Well, good morning, everybody. This is Jomo Stewart here at the Fairbanks Economic Development Corporation. It is Tuesday, March 19th, 2024, just after 8 a.m. And we're here for this week's Energy for All Alaska Task Force. Our guest, very special guest, is Mr. Phil Kaluza.
Kaluza. I've been called a lot worse.
My favorite name is Jomo. It's the hardest 4 letters in the English language, apparently. Probably because it's Kenyan. Here to discuss air source heat pumps. So just a couple of announcements right here at the top. So it is Housing Action Week, brought to us by our friends at the Cold Climate Housing Research Center. If you haven't checked it out, they have just a breadth of amazing content for us on the housing issue, this pressing community issue, and frankly pressing for across the state of Alaska, our high latitude environment. But so if you haven't done so already, go ahead to the CCHRC website. You can just Google CCHRC Fairbanks, and you can see the whole range of scheduled events. Yesterday, there was one on housing justice. There was a big open house. If you've not seen the CCHRC NREL facility, it's amazing. You can also schedule with the executive director, who is here, Miss Mindy O'Neill, if you'd like to have a further tour. But again, it's great content all week. So do check it out. Register for any events that need it. I don't believe there's any cost associated. They just want to know how many lunches to buy. I guess the other thing is, so a couple things. As usual, I do not have my second. Oh, John Davies is here with us. Dr. Davies. I do not have my second screen, so I'll be doing my best to monitor chat, but no promises. If you have any questions, any comments, as has become customary, just go ahead and throw up your hand, or really just take yourself off mute and fire away. We like to maintain that conversational format, and it is for you. Finally, I have forgotten my cell phone at home. So if you're one of those people who's habituated to texting me to ask your questions, sorry, you're not off the hook today. You'll have to go ahead and ask your questions. All right. Well, without further ado, sir, I will hand the floor over to you.
Okay. Well, good morning, everyone. My name is Phil Kaluza. I guess I should have had Mike Music do my intro. He did such a great job yesterday. But I've been around Alaska for a long time, lived in Nome for 17 years, got involved in the energy efficiency world and Alaska Craftsman Home program, and been kind of moving ever since. And now I'm living down, pretty much retired, living in Seward, and I sort of got involved in heat pumps about 10 years ago, and I can kind of show you why. Seward was kind of a nice special place to get going with heat pumps. And so we've been putting together a presentation here for a while. I got a lot of extra slides that I know I don't have time to get through, so we'll clip along, but please, let's get the questions out. This is for you, not for me. So I guess with that, why don't we just kind of mosey on. I put a little note there. I've been on the Rural Energy Efficiency Board forever, and they actually made it an attempt to sell some heat pumps and other products, but just to let you know in case you see something that I'm not here to really sell. Now what happened?
Now, we did have a presentation several months ago on research results relative to ground source heat pumps, right. Mostly ground source heat pumps. So just know we're a little bit not totally green on the subject.
All right. Okay. Yeah. And I'm not here to say that air source is any better than any other source for heat pumps, whether it's ground source or Sea Life Center down in Seward is using seawater. They're moving millions of gallons of seawater through their facility anyhow, so they're stealing a few BTUs out of that water. So, I mean, all this technology is very similar. It's just really it's time to do some economics and decide what fits best for your needs. But air source heat pumps is by far probably the most economical approach, but maybe not the most cost effective for your application. So we'll give you a little rundown of what air source is, and you can do your own research on the other options. And so really, why are we here? I mean, they asked me to come up because, Fairbanks have been dealing with your air quality issues forever. And, we can stop burning oil. It's good for your local environment, good for the global environment. Hopefully we can show you where you can save some money on your heating bills. And, you know, in Seward, we get municipally owned utility. Here, you're still a local co-op, so do you want to support your local electric co-op, or do you want to support big oil? I guess is kind of one of your options, because you know, you're gonna use more electricity, which really helps everybody's electric bills in the long run. Yeah, I just kind of did a quick search, and things haven't changed much over the last 20 years. You still have your issues, and it was interesting that this study that finds home heating fuels a direct source of sulfates, ultrafine particulates in winter air. That just came out weeks ago. That's very timely. But you guys understand your air quality issues far better. The idea is if we're not burning oil down in the bowl, and we can be using electricity there, and unfortunately we got to generate that electricity, but if it's not contributing to your local air quality, that would be great. This just came out. The Northwest Arctic got a grant to put in 850 heat pumps north of Kotzebue, in the villages north of Kotzebue. I'm going, now this is going to be a challenge. They got some interesting environments up there to contend with, but again, their dream is to get enough windmills and solar up to power a heat pump. That would be ideal, is to be able to use renewable energies as we proceed and heat our homes. There's a little picture. I just wanted to make sure when we talk about air quality, I know Fairbanks has had their summers of smoke. And there's nothing nicer than that little mini split that you can close up all your doors and windows and turn on your mini split onto air conditioning, because they work both ways, so both heat and cool. So those couple weeks in the summer when you just, it gets really bad, it's kind of a nice blessing where you can keep your indoor air quality better than the outdoor. Oops. So what is a mini split heat pump? On the left, you see the outdoor unit. It's really essentially just a big fan with some coils wrapped around it, and a compressor as part of the refrigeration cycle. And from there, this warm refrigerant in our heating mode goes to that. On the right side, you see that little head, we call them indoor heads. And that's essentially another little fan coil. There's coils in there with a very quiet fan. And so we're transferring that heat that we created or gathered from the outside unit and brought into the indoor unit up here. And those two talk to each other and works pretty well. So they call it a mini split because you do have an outdoor unit and you do have an indoor unit, unlike a window air conditioner, which is kind of a combo deal. Some mini splits will come with several of these indoor heads, so you can direct heat to several rooms at the same time. They come in all sizes. There's a little tiny house on the left there with one sitting on the tongue of the trailer, and I don't know where this picture is, but I think it's going to be my retirement home, wherever it is. A lot of research going on there. So what is a heat pump? Well, heat pumps do not generate heat. As the term implies, they're moving heat, just like these water pumps are moving water. They're not making water, they're just moving it. So there's no free lunch with a heat pump. We're going to have to supply electricity to pump that, to move that heat through that refrigeration cycle from the outdoors to the indoors. What I like about this photo is, they're all just kind of moving water about 4 feet or 5 feet up. But if that second pump to the right had to go up 20 feet, had to pump water up 20 feet, well, that pump's going to be working a lot harder, and it's probably going to be moving less water. And if that third pump had to go up 50 feet, again, it's going to be, working as hard as it possibly can and not moving as, less water yet, because that lift that it has to go through creates more work. So it's very much the same with a heat pump. The colder it is outside, the more work that it is for that heat pump to actually extract that heat from that outside air and get it warm enough to be usable inside the house. And so we'll see how efficiencies are affected and the amount of output we can get from a heat pump based on outside temp. But again, we're not directly burning fuel to create heat. We're just moving it. So here's an example. What we're doing here is we're taking 1 kilowatt of electricity and putting it into this heat pump. And it's able then, on a fairly cold day, to extract 1.5 kilowatts of heat from the outdoors. So the combination of what we put into the heat pump and what it got out of the air, we're generating 2.5 kilowatts worth of heat. And if you look, and the way they deal with that is they call it the COP. It's a very common term you're going to see on any heat pump. That's called the coefficient of performance, or it's the efficiency. And so it's saying for every unit of heat we're putting into that heat pump, we're getting 2.5 units out. So essentially it's 250% efficient as compared to, say, your regular electric resistive heat. There we're just putting 1 unit of electricity in and just getting 1 unit out. So in a lot of ways, we could really just call, these heat pumps, they're electric space heaters, just very efficient. Here's another diagram of the basic refrigeration cycle. Essentially, it's this compressor that's compressing that refrigerant gas. And you have a coil on the inside and a coil on the outside. And to make them more efficient, they put fans on those coils to extract the heat better. We need this expansion device to play the refrigeration cycle and changing pressures. So it's, it really is the exact same thing on the right here. This old refrigerator really had coil on the inside of the freezer wrapped around, and it had coils on the back of the refrigerator to get rid of the heat out of that freezer compartment. And down below is that little compressor. Now the refrigerator only worked one way, whereas a heat pump, because they put this reversing valve in there that basically redirects the direction of the flow. The heat pump itself doesn't really care which way it goes. And one thing I really like with heat pumps is if we look at sort of the theoretical maximum of our heating, oil heat, we're pretty much as far as we can go. There's a couple percent of heat we're losing still, but we need that to get the gases out of the chimney system and stuff, and gas. So we're at almost, we're done with what we can get out of heat for these oil and gas systems. But if you look at a heat pump, theoretically, it could be 1,300% efficient. Right now, we're down here at 200 to 300%, and maybe over the last 20 years, we've gotten that extra 20, 30% out of this thing, or 50%, a little chunk. So we got a long ways potentially to go, but it's going to require new refrigerants, a whole new kind of compressor technology and stuff. But so I just see the future of heat pumps just continuing to get better and better. A little more lingo, we have air to air. That's just basically it's an air source heat pump. So it's going from air, and it's taking that refrigerant into the house then and running it through fan coils and creating warm air. We also have air to water heat pumps that basically take that exact same refrigerant, same outdoor unit, but instead of making warm air, we're just making warm water with it. And then the ground source world, where we can be extracting heat from the ground or water type thing. This is interesting. I hid some slides in here that are showing up now. So again, we talked about the COP, just some of the lingo that you'll see whenever you read literature and stuff. This coefficient of performance, that's the efficiency of the unit. How much energy do we get out divided by the energy we put in. The other big term in the US is HSPF, and that's the heating system performance factor. So that's designed to kind of give you the seasonal average for a region. Well, the original one was Region 4, which is like South Carolina or something. So just recently now, they basically have redone this system a little bit, because it was always a little, maybe a little too for I don't know, positive or something, or they're overestimating the savings from heat pumps, and so they played around with it a little bit and go, okay, it's kind of sort of like the miles per gallon originally from EPA. They were so far off, and over time they finally tweaked it to the point where real driving is kind of getting close to that. So
with the actual particulate outputs of wood stoves.
yeah. Yeah. So Region 5, so now they basically, we got this new HSPF2, which you should be looking for. And they have Region 5, which is the northern part of the US. And one of the issues is heat pumps are always for cooling in the southern states. And so all the standards and everything that they use were all based on cooling. And now we're going, wait a second, if we're using these for heating, let's kind of adjust how we're rating these things and stuff. So that's HSPF Region 5 gets us closer. And really, to me, the most exciting is the EPA in their Energy Star program. They have now created a cold climate certification for heat pumps. So there's a slide that kind of lists a couple things that requires, but that's at least telling us, okay, somebody's serious, that they've actually done something and tested their heat pumps to cold temps to confirm that they're working. Those in the old day, in the refrigeration days, you bought heat pumps by tons for cooling loads. And 1 ton is 12,000 BTU. So you might see a 12K unit, an 18K unit, and that's implying how much heat output we're going to get for cooling.
I would just remind everyone, while we have a moment, I saw someone's hand was up for a moment. Again, we're trying to monitor things like hands and chat, but it's a challenge. So if you do have a question, please, you're not being rude. Just go ahead and take yourself off mute and fire away. Thanks.
I do have to take a breath once in a while. So. Yeah, so this site is pretty interesting. It's the NEEP, it's the Northeast Energy Project or something, and they maintain a database essentially of all the heat pumps. And so if you want specific data on, what the heat output is of various units and their ratings and certifications and stuff, this is a great site to go to. Interesting how 5 years ago, there was only, 50 systems listed. Now there are hundreds. I mean, so everybody who makes heating and cooling products now is basically selling a heat pump. Now, whether I assume most of them aren't making them, they're just rebranding them. But so a lot left to kind of figure out for a consumer.
But they're doing like independent testing and.
Well, that's still our problem. Most of essentially all the testing is still manufacturer provide testing. So it's all self-certification world. So buyer still needs to beware.
Are they providing again a little bit of that independent?
So they are.
Hey, Phil, this is Mike. There's some exceptions going on now. It's cold climate. Housing Research Center is testing heat pumps and have been for some time.
Now, if they can just publish that data.
Right.
Yeah. So here's a couple graphs that just kind of remember I was saying how as it gets colder out, we're losing performance, we lose efficiency, and we lose output. So here's an example here. Here's outdoor temperature down here in the bottom, and this is the heat output on the left. And you can see as it gets colder and colder, our heat output kind of declines because that heat pump has to work harder and harder to get that heat out of that air and lift it all the way up to a usable temperature. But it's not falling off the cliff. And so this Fujitsu model here, they're rated down to 15 below. Now, and that's just a rating. They don't say it dies at 15 below, but it's probably the coldest they had a freezer to test their units at. I know CCHRC has been testing some far colder during your cold snap. So You know, the refrigerants that we use, you know, probably play a role in where all this stops. On the right side, so that was the heating output, and you notice your efficiency falls pretty much identical to that output. The colder it gets, the harder the heat pump has to work and the less efficient it is. So we're gonna spend some time looking at, well, how cold can we go and still be economical? That's probably the biggest question, so let's make sure we get that answered. But this is just the relationship, and it just, you know, it's unfortunate, you know, when you need the heat the most, you know, a heat pump is actually losing some of its performance, but you just got to factor that in. So as a quick comparison, when we look at COPs, we look at a ground source heat pump. I think this is data from CCHRC's ground source heat pump. You know, it maintains a fairly steady efficiency throughout the year because it's getting its heat from the ground, which is very stable, as compared to an air source heat pump, which we noticed at cold temperatures is far less efficient than at really high temperatures. So one would go, well, ground source is better. Well, it is. Unfortunately, it costs a lot more too. So again, it's back to doing some math. And as a comparison, a COP of 1, that's essentially what an electric resistive heater is. So you can see where in this example, it's saying, well, an air source heat pump is actually, you know, minus 15. It's still doing as well or better than electric resistance heat, but not much. And you're working that poor heat pump really hard. It's kind of a question of what do we do down here in this really cold temp? The heat pump works, but is it, you know, economical to be operating it?
Is there an average COP that you look for when you?
Yeah, kind of, well, that's that HSPF, but it's, you know, it's for the warmer, a little bit warmer climate. I wish they'd give us a region 7 or 8 kind of deal.
Right.
And then we'd be able to just use that number. But that HSPF, you know, we can at least look at it because the higher the number, the more efficient they're saying that heat pump will be in your colder climate. So we can just use that as a relative comparison, I guess. So how cold can we go? Where it's economical, what are we doing? Oh, you're gonna move that?
That's what we
Okay,
see.
yeah. So if we're looking at, you know, we were playing with 25-cent electricity a day ago, only to find out that your rates jumped up to 30 cents a kilowatt.
So we know it.
Which is bad for heat pumps because, you know, the price of electricity in relationship to the price of oil is very important in terms of the economics. But somebody had noted they just bought fuel oil for $4.45 a gallon, so that kind of bumped up too. So playing with our numbers in this heat pump calculator that Alan Mitchell with Analysis North put together for Alaska that has all the Alaska communities in there, the weather data and stuff. Playing with that, we kind of found that in Fairbanks, around 8 degrees was kind of the cutoff, the economic cutoff, or where a heat pump is still efficient. And that had a COP of 1.95 or 2.
And part of the driver on that is the electricity cost.
Right. So if electricity was, yeah. If electricity was cheaper, if we had this higher, that's fuel price, and electricity was cheaper, we'd be able to go colder and the economics would still be better. Or if the price of oil went up, the economics is better. And the reverse is true as well. So here's Fairbanks. So if we were looking at that 8 degrees, well, how much heating can we do? Well, it kind of means we can get just about 50% of your heat load for the year with a heat pump.
Hey, Phil,
Yep.
you have a comment in the chat I think it's relevant here from Gary Newman, who's on our Golden Valley Board of Directors. He says the June 1st, the 4.8-cent increase on the bill is expected to drop significantly, making heat pumps certainly more favorable.
Okay, well, good to hear. Good to hear. So we can take that as a positive note down the road. Yeah, so I hope this graph kind of makes sense. You know, unfortunately, because Fairbanks is gets kind of cold in the winter, it's hard to deal with that in 20, 30 below world. But you also have a whole lot of heating going on above 8 degrees, so there's still a lot of potential to save.
So does that suggest hybrid systems?
In terms of like a hybrid between a ground source and air source? Oh.
Just not, oil and.
Oh, yeah, you're pretty much committed to have some alternate source of energy, I think, for the really cold.
I mean, part of what we got out of the ground source heat pump discussion, at least from my recollection, was, yeah, you would still end up using your furnace, your oil furnace, but you would radically reduce the amount of time you need to use it. Yeah. Balancing one of these kinds of systems.
I mean, again, it's kind of just the economics and, to put in a system so big that could take care of your, even if the heat pump could run down to 40 below, the efficiency, the economics are still there. There's no free lunch. And so it's,
this is an interesting graph. Again, how much of a year or the temperature span is above the minimum
between
use rate.
If you set the 8 degrees, and this is sort of kind of our, not a bad target, because to try to get more of this means you have to put in a much bigger heat pump. You're gonna spend a lot more money to deliver that more heat. And the bigger units, for whatever reason, are less efficient than the smaller units. So well, the economics get kind of interesting is I can put in a bigger unit in here and I can, capture a little bit more of that oil heat with the heat pump, but the economics actually will get worse. So, so here's some real data. We, that cold snap you had, even Seward, we got down to 5 below. And within 2 weeks, we were already up to about almost 40 degrees in these cars. So just some real data, and these are the COPs that I was collecting. So again, down around 8 degrees. If I look, my heat pump is just around a COP of 2. So the heat pump really doesn't care where you're at. It just wants to know what the temperature is outside. So whether you're in Maine or Seward or Fairbanks, 8 degrees is 8 degrees to the heat pump. Anyhow, it's always fun to play with real data. So I've been gathering data on, I don't know, I think I'm on my 4th or 5th different heat pump now in terms of my own little personal research going on. So here's why I got excited in Seward when I got down there with heat pumps and all this new technology. If you look at Seward's heating profile, relative heating load, we have very little down here in the really cold. So it's pretty easy for us to design a heat pump to pretty much capture all of the space heating needs in Seward. But if we look at Fairbanks, you've got all of this stuff, that's much colder. But, you look at how much heating goes on from that 8 degrees, in the cool summers and everything that go on, really the total amount of heating that you're doing isn't much different than Seward. It's just that very cold temps, you're gonna have to rely on another heat source. Just a little discussion. So, we're using that 4.45 a gallon delivered for heating oil, but what is the real cost? What is the cost for your outdoor air and the health issues? I have no idea. I'm not one of those folks who can somehow equate asthma rates to the dollar value, but certainly there's a value in trying to improve our indoor and outdoor air quality. A heat pump just doesn't backdraft. It doesn't smell like fuel oil. It just kind of does its thing very quietly. And so the whole planet health costs. So, what about CO2? That's kind of a big deal. Well, we did a quick calculation. So burning a gallon of diesel generates 22 pounds of CO2. What's it going to cost us to get that CO2 out of the air? Well, grabbed $100 as a nice round number. So that's adding $1 a gallon. If we were just looking at the cost of the CO2 that we're adding to the environment. Now, we're not including the generation cost you know, to make that, the electricity, but.
When we say 22 pounds per gallon, that's the all-in CO2, again, from production and transportation.
No, that's just burning it in your boiler. I mean.
But I mean, a gallon of water only weighs 8 pounds.
Right,
So a gallon of fuel oil weighs what, about 7.5?
Yeah. so
Like,
basically,
I'm not saying you're wrong.
right,
I can totally see it on the all-in cost,
Us.
again, development, transportation, processing. It's, yeah, that's a intensive process.
Right.
And then plus you're making CO2 when you
Right.
combust.
So when we start looking at economics, I mean, you may be going, okay, well, when I look at those graphs and decide how cold I'm willing to go, you know, if you want to add these other costs there, it's going to allow you to, you know, justify running your heat pump at lower temperatures.
The cost of negative externalities.
Yeah. So here's another little graph that friend Alan Mitchell put together, and basically it's showing on the very left is the equivalent price of oil, and on the bottom are our electric rates. And then all these lines correspond to different efficiencies of your heat pump. And so this 2.5 is a pretty, you know, I think that's in our ballpark of what we'd see over the course of a year using a heat pump in Fairbanks. So this example is 25, you know, right now you're at 30 cents, but if we're gonna be going back, we're looking into the future, folks, we're not thinking. So if we go back to this 25-cent kilowatt rate, we read up to what we think our seasonal COP is gonna be, we read across, and it's saying what, 3.20 a gallon or something. So that's the equivalent cost of running that heat pump at that electric rate. And if you're at $4.45, that's over $1 a gallon less expensive. So there's some economics there.
Well, and Gary, Director Newman of GVA just promised us we'd be at 25 cents in June.
Right, so Mike was going, well, we ought to be used 30. Well, okay, now I'm back to 25, which is where we put our little dotted line, so.
Hold on here just a second, guys. This is my optimism that Lord knows it can't get any higher, but
Right.
No, I told you, I'm just
Yeah,
kidding.
yeah.
some of it related to the.
Yeah, we're gonna vote for 20 cents. But you can see. Yeah.
This wasn't a promise from me. This is just my.
I know, Gary.
So, but if we looked at 30 cents a gallon, you can see what the difference is. If we went up to that same efficiency line right across, now we're more like 3.80 a gallon equivalent. So it's still some savings from, you know, current price of oil, and what the price of oil is going to be in a week or a month or 5 years, I have no idea. I'll let you guys play economists. Kind of another.
But as Mike Music points out, there's probably a connection between those two, because a lot of our marginal heating
Is gonna be-
energy production is based on the price of oil,
Right.
right?
So really, if we're adding a heat pump to your load, it's probably gonna be generated until we get the windmills
right.
spinning.
Right.
Which again, would be ideal to have that north wind heating your house. I like that concept. Here.
In Delta, it's the east wind.
Yeah. So here's where we kind of converted those COP lines, so looking at outdoor temperature. So again, if we were looking at 0 outdoors, 30-cent kilowatt, or we'll go to the Optimist one. So here's at 30 degrees, basically, you know, a little over $3 a gallon. But you know, if we wanted to get down to 0, all of a sudden now we're at $4.50 a gallon equivalent. If we went up to this next line of 0. So that's kind of a break even. Again, we're kind of looking at that just above 0 as being, so your break even economic temperature. So
If we may, sir. Hey, Clark, I see you jumped to the top of the participant list. Did you have a question?
Nope, have no idea. Must have been my interest. So nope.
Okay, yeah, we can't see hand raises with this view we've got right now. Okay, thanks, sir.
So, and you know, it'd be nice if somebody wanted to we can print these out or something and get those to you. So one of the other air source heat pumps, and I know there's a lot of interest in the hydronic world, how can I connect an air to water? And if you look at it, the outdoor units are essentially identical to the mini split or the air to air systems. You know, again, they're collecting that heat out of that cold air, but now instead of turning it into warm air, they're basically running it through a heat exchanger and making warm water. So, and again, the same performance curves and everything pretty much apply. I guess the one big issue that I have with most of these heat pumps is they're called monoblocks, and I think I might have another slide there, but it means everything's on the inside of this heat pump. The good news is you don't need a refrigeration guy. All you need is a plumber to hook up piping, water pipes to it. The bad news is you got to run these water pipes to the outside, which means glycoling a system and creating a separate loop, you know, to isolate that from your domestic water systems and stuff. And what I have in my house in Seward is a split system, just like the mini split. It's split, and I'm running refrigerant into a box. And I got a picture of that here someplace down below it. And so I'm not bringing water out to the outside. I'm doing it all on the inside. But you know, I need a refrigeration guy then to run those refrigerant lines into the inside of the house. This is kind of exciting. What's going on now in the air to water world is they're using propane as a refrigerant. Because they're trying to get away from the nasty refrigerants that created, you know, destroyed our ozone levels. We got rid of those, but now the current refrigerants, you know, still have very high levels of global warming potential. And so getting to propane, we're getting down to just about nothing in terms of risk. They're rated to 15 below. They make a little hotter water. And so you're going to see a lot of that. But again, there are all these monoblock systems, which just adds that interesting dimension of running even glycoled water outside. It just kind of makes one nervous. So hopefully we can get CCHRC working on some solutions to be able to use this new technology. So here's my unit. You know, again, it looks outside. It's boxy because this unit was designed to either be a monoblock where everything is contained inside this side. But in mine, I'm running these refrigerant lines to the indoor to this little box. And all it really has is this large flat plate heat exchanger transferring the heat from the refrigerant to a tank that I have. And this little circ pump then is pumping water from my little buffer tank through that heat exchanger, pulling that heat out from the heat pump. But almost impossible to find in the US right now. All the manufacturers make these, they just don't sell them in the US. But it's coming, it's coming. I've been saying that for a while. The other air source world is heat pump water heaters, and they're actually gaining some popularity. It's essentially an electric water heater, and on top they put a heat pump. And so what they're doing is they're taking air from inside the house, inside their utility room, where we have this thing put, and they're stealing heat from that air and turning it into hot water. So therein lies the rub. We're taking heat from inside the house, which means in dead of winter, we have to replace that heat. We could be doing it when milder temperatures. We can actually let a mini split that you may have installed, and that can make up the heat. And if you play with the numbers, you know, the water heater in the summertime, this heat pump water heater has a COP of about 3, say. So for every kilowatt of electricity I put into this heat pump, I'm getting 3 kilowatts worth of heat into my tank. But when we got to make that up with the heat pump, the net efficiency is more around 2, which is still, you know, twice as efficient as an electric hot water heater. But you got to think about we're moving a bunch of air, make some noise, so where you can locate these things, it's gonna be critical. If you put in a small boiler room, you'd probably get the thing down to freezing in no time. So it needs some space to work. So it's kind of, limited, I think, in where we can put them, but it does have an application. Obviously, if you're in Florida and you need air conditioning, I mean, why not? Let's just make our domestic hot water instead of dumping that extra heat outside, let's put it in the tank. But that's just more technology coming our way. So how do you pick a heat pump? We're still recommending, I don't know what all those other brands are. I don't know who makes them. I don't know servicing and stuff. But a lot of these popular brands, Mitsubishi, Fujitsu, Panasonic, Daikin, there's a lot of models. And a lot of it's gonna come down to, what your installer and service guy likes, working with, so. And again, keep this Energy Star cold climate rating in there. That thins out the crowd significantly in terms of what you're gonna be looking for. And the higher that HSPF number, the better. A little more bigger is not always better with heat pumps, because I found in our first mini split that we tested, it was oversized, and which was supposed to make it more efficient. But it turned out the thing cycled more than it ramped down, and so cycling is just brutal. I mean, you think your oil boiler hates cycling, heat pumps in terms of efficiency really hate cycling. So, to put something huge in your house, hoping you can capture a little bit more of that cold heat load, maybe you may be suffering from that during the whole rest of the other year. So we kind of look at, 50% of your design load. If you can reach that, you're probably gonna get to that 50-60% in Fairbanks. In Seward, warmer climates, we can get up to 80%. A lot of slides here I wasn't showing, but that's all right. So a little more economics, in warmer climates, if we're sticking to above 8 degrees, it takes like 12 to 13 kilowatts of electricity to save that gallon of oil. So you just remember that 12 kilowatts, and as the utility plays with their price of electric and stuff, you can just kind of do your simple math in your head. And again, you can propane, if you're heating with propane, heat pumps are just a no-brainer. If you're heating with straight electric heat, a heat pump is a no-brainer. If you're burning wood, it takes 1,300 kilowatts to equal a cord of spruce wood. Again, you can multiply that times the cost of your electricity now and decide what's cheaper. Again, we're just kind of doing some more math here. I'm gonna skip through some of this stuff.
Actually, if you could go back to the Bush economics just for a moment.
Which
Next
one
slide.
was that? Too far?
Oh, yeah,
Too far,
it's-
yeah.
Keep going. That one.
That one.
Okay.
So in the bush, where they have PCE, I mean, actually heat pumps can make a lot of sense if you're staying under your PCE rate. If you're paying $8-10 a gallon for oil, and you've got some extra PCE, credits coming on your electric bill, the economics are very good. But if you're paying 80 cents a kilowatt for your electricity, then it kind of turns out the economics are pretty much the same as Fairbanks. Yeah. Again, it's that ratio of, the cost of electricity to the cost of oil.
Thank you.
So that, okay. Maybe, and carbon impacts, you kind of look at, a heat pump in terms of CO2 production. And if we went to more renewable energies and stuff, how much better the heat pump is relative to all these other sources of heat. It's interesting. I don't want to get into this discussion about burning wood and whether or not it's carbon neutral or carbon negative or carbon positive. It kind of gets down to, well, if you didn't cut down that tree and burn it, how long would it have taken for it to rotted away and produced the same amount. And if we're trying to get rid of our CO2 within the next, 50 years. Yeah, again, sizing too big. I just can't overemphasize that. And unfortunately, heat pump installers, just like oil service people, they're always gonna try to sell you something bigger than you really need. It's just universal. It isn't any different in the heat pump world. So it's kind of like, no, I don't, because the bigger units are less efficient and, the cycling issues and stuff that go on. So it's time to keep those guys under control. So again, this whole refrigerant world, that the stuff that we made that was destroying our ozone, all these synthetic refrigerants, they work great as a refrigerant for doing their job, but they're just bad on the environment. And these refrigerants will leak out of your systems over time. So the goal now is really they've kind of got the efficiency down until they come up with some whole new technology for compressors and stuff. Now they're moving to what's better as a refrigerant. Well, I mentioned propane is become a new popular one. Unfortunately, the problem is it's very combustible. And so they don't want that, they don't want you piping that inside the house. CO2 is very, Japan's got a lot of these units where they're actually using carbon dioxide as a refrigerant. Little more complicated dealing with CO2, a little higher pressures and stuff, but they're kind of the baseline of this global warming potential, GWP. They give that a 1 and compare everybody else to that. Well, the typical refrigerant that we're using in mini splits now, it's called 410A, that's over 2,000. And the really bad stuff that we banned over the last 20 years used to be, almost a magnitude worse than that. So this whole progression into trying to find refrigerants that are comparably efficient, but are not as environmentally bad is sort of where we're heading. And integrating some more controls with existing systems is kind of the big push right now as well. So, see, I was hiding this, but that's okay. So this is our first little mini split that we're monitoring, Alan and I, and we're kind of doing a co-heat on my apartment. So we're heating the apartment with straight electricity and monitoring that power use compared to the heat pump power use. And so as it got down at 10 degrees, but as it warmed up, the efficiency was improving, the COP, and then something bad started happening here. And the bigger the bubble represents, the more cycling that was going on. And this thing was just dying on me as it warmed up. I mean, this thing should be skyrocketing. Well, of course, I complained, and Fujitsu got me a tech guy, and he sent me some old wired controller that got the temperature sensor out of that indoor head. And it helped a little bit, but this was not doing what it was supposed to do. Here's what the manufacturer, this green dotted line up above, this is what the manufacturer spec said my heat pump was going to do. That HSPF number was saying, well, I should be around here. Well, obviously I wasn't getting there anywhere close. So we put in a much smaller unit, different brand, and it's a little closer to meeting the manufacturer specs. But so again, sizing is critical. And here's this calculator that Alan developed, and he's using a lot of the ACWARM home energy rating database stuff. So for every community, it has all your historical weather data that he can be putting his heat pump into your data. He's got fuel cost data that may or may not be, they upgrade it every 6 months, but obviously things change quicker than that. But so to get to that website, heatpump.analysisnorth.com, in case we don't get a chance to play with it, but I hope we can get to it.
It looks like we are getting near the top of the hour. If there was anything.
Yeah, has anybody got any questions right now? Anything they want to add?
Yeah, I do. We have some large public facilities. We got a fish hatchery, and we have the Carlson Center, which is an ice rink, and we have a hot river running by it. It strikes me that we could heat and make ice and warm the water for the fish, all using heat pump technology, and cut our fuel bills in half. What would you
Oh,
say about that?
absolutely. I mean, you know, if you've got 40-degree river water, I mean, that could be way better than your ground source, I suppose.
I wonder why
And
we're
it's
not
just
doing it.
distributed from, you know, from the site to the buildings, I guess.
It's right on the river.
It's right on the river. Yeah, I mean, why not?
That's what I want to know. Why not?
You know, like down in Juneau, you know, their whole airport, they put some wells down there, so they're getting, you know, a little warmer seawater temps to basically heat the airport, and the aprons and all of that work is all being done by that, essentially that water source heat pump. So no, that'd be some fun numbers, Mike, to show. Now, I don't know what their electric rates are and stuff, but good idea.
GVA.
Yeah, so here's just a slide of some of the little monitoring stuff. This is my original heat pump straight from China. That was the old technology. This next one is the newer technology with the variable speed, you know, better, higher performance compressors and stuff. So these two are air to water. And then this was that Fujitsu that kind of just died on me when it got warmer out. And this was the little Gree the smallest one I could get. You know, obviously it was doing much better as it got warmer. You know, it's interesting, if Fujitsu started cycling, but it kept that temperature really nice and precise. You know, if you were set at 70 degrees, it was just plus or minus a degree. The Gree said, oh yeah, we know the cycling is really bad, so we're gonna let it, kind of like a Toyo stove. We really don't want to shut off unless we absolutely have to. So they'll let the temperature rise 3-4 degrees above what you have it set at. You know, so it might go up to 74 degrees and then cool down to 68 and go, okay, and come back on. So it's trying to maintain these longer cycles so it wasn't damaging. Well, you know, if you're used to those temperature swings, you know, that's fine, but I mean, and it is only happening at the warmer temp, so it's not like the 20 below where you might notice it more. Anyhow, it's all, you know, it's kind of fun to see what's going on. This is sort of gray code stuff compared to what CCHRC is doing, but data points. So now I just kind of wanted to show you some of the installations that, you know, just pictures again. Here's that one, here's the
My
outdoor.
only concern with that configuration, heat rises. And so if it's blowing in heat that high on the wall, I
So
wonder how it's gonna be down,
right.
you know, to these.
I hear you. But it turns out these fans do actually move quite a bit of air, so that air does blow all the way down to the floor. I mean, really, so what's critical is, you know, in this application, you know, this is not hot air, and, you know, I know Fairbanks isn't in a scorched air world either. They're, you know, you're hydronic, so, but these heat pumps, you know, they blow warm air, 110 degrees, but you really don't want this air blowing on people who are sitting. And I'll show you a lot of pictures. Now, these things come where you can adjust these louvers, so they actually could be moving that air, you know, off to the left there, you know, blowing it more over this way and not blowing directly on people's houses. Now, you know, what's interesting is these high-end, they kind of generated these new high-efficiency mini splits, but they only come with this wall unit. So these have to match. You can't take a different brand or different type and put, you know, a different coil on there, because there are other less efficient mini splits that give you a floor unit. So you can have a nice robust floor unit on there, but they're not the high efficiency units. And so and then you're playing the economics of the efficiency world. I'll show you a couple pictures of that. You know, here's another application, a nice, you know, you're putting it in as big an open space as you can so that he can get around. And you're not blowing it on the kitchen tables or on couches and stuff, and so that's kind of a nice application. And here's one that's kind of out of the way a little bit, not gonna be creating any drafts. This is my little apartment one, I got it stuck between two windows. And the upstairs of my little apartment doesn't have any heat, and it's got an open stairway, but you know, it just doesn't get warm enough. Go, wow, geez, if I could be sucking that cooler air into my unit up here, it'd make life more efficient. Maybe I get more heat up into the upstairs little bedroom area there. And so you spend a whole afternoon cutting in that grill up above there. Only find out I didn't do diddly. So, and not all experiments work.
You need a little fan.
But that's exactly what I did. I put a little muffin fan in there and that worked.
Yeah, yeah.
You know, of course, now I had this whiny little fan right next to your bed. So I never quite accomplished it, but anyhow, you know, it's a lot of applications. And the whole goal, what you need to figure out is, you know, we gotta run refrigerant lines from this guy to the outdoor unit. So where you put your outdoor unit, which needs power, so, you know, now the electrician's gotta decide where it makes most sense to put the outdoor unit to simplify the electrical part. And then you gotta connect these two. So your options sometimes get a little limited. And where you can put it, it's always.
Are these typically 110 or 220?
They're typically 240 volts, 20 amp kind of breaker world, so you're gonna have to, if I have a couple slots on your panel and if your panel's already maxed out or over max, now that's something you wanna know right up front. Cause when an electrician says it's gonna be another $5,000. You might have to be thinking, yeah, but there's rebates and stuff for doing some of that.
If I may, sir, I was just gonna check. I do see a few more popped up in
Ah.
that.
Okay,
Water temperature in China.
I like the China idea. Now, of course, you don't want ice, dams destroying your tubing that you got buried in the river. And there's a few technical issues to.
Well, it's where Aurora is spilling. It's
The heat, right.
Yeah.
Now, I would want to get it right out of that pipe before it even gets to the river. Let's get that heat.
Okay. All right, well, sir, again, we are nearing the top of the hour. Just one final reminder, again, for everybody. We are, this is for all of us. So if you have any final questions or comments or wanted to zip through to see stuff, just go ahead and let us know. Mike, I see that you are visible.
Yes. Can you tell us a little bit about the tax credits and rebates for businesses and nonprofits and so forth that are available that will almost pay for installing heat pumps?
So I'm not as familiar with the business side of things. On the residential side, we have that Inflation Reduction Act that, the rebates for heat pumps for like mini splits, the lower income, the 80% average household income, in Seward, that was like 55,000 or something. So if you make less than $50,000-$60,000, and there's a number of people in a household kind of plays into that, but you're eligible up to $8,000 instant rebate on a heat pump. So that could mean, that might mean 2 heat pumps kind of deal for lower income. If you're middle income, from that 80% up to 150% income, which most of us fit in, that's a 50% rebate up to $4,000. So if you spend $8,000 on a heat pump system, you get $4,000 back. And it's supposed to, the plan is to be at the time of sale. Now, AHFC is going to be the one to come up with, to fine tune all of these requirements. So I don't really want to, guarantee somebody until AHFC actually comes up with their final rulings. But yeah, so there's some big rebates up to $8,000 for heat pumps. And You know, there's rebates for that heat pump hot water heater. If you think you know, got a semi-warm garage that you can, you know, make work or something. I'd love to see some of those water heaters go in just to, somebody's gotta do it.
Data.
Somebody's gotta do it. CCHRC.
Well, I was about to ask if we had any accountants online,
Right.
but you noted that, for some of these credits, it's supposed to happen at point of sale.
Right,
So
I mean, that's
it's
the
on
goal.
seller.
Right.
That,
Cause they're really, you know, the lower income, I think it's great, cause they don't have $8,000 to, you know, pay the installer and wait 4 months or 6 months for a rebate, so that.
so I'm lower income. Okay.
Yeah, yeah.
Well, and there's
And even-
also, what,
right.
the FNSB wood stove change-out program
Right.
has some funds, to help
Really?
support this as well,
Okay,
and other transitions, if I'm not
Right.
mistaken.
But you have to be, you have to be taking something out.
right.
Right.
Yeah, so-
And so, and there's up to $2,000 tax credit, I believe, for
Right.
heat pumps as well. That's available right now. And so if you're gonna spend $8,000, you get this $4,000 rebate. You also get the tax credit, the 30% tax credit on that other $4,000. So you get to knock that down a little bit more as well.
Hey, Phil, this is Gary Newman. You know, good to see you again. It's been
Yeah.
far too long. How noisy are the fans inside?
All these indoor units are, I would call them extremely quiet. I mean, they really, you know, I think my HRV makes as much noise as just that background noise. So very, very quiet. I mean, it's a fan. Really, the noise is on the outdoor unit.
Okay, so
You know, that's where the
don't put the outdoor
compressor
unit
is.
on, don't put the outdoor unit on your bedroom wall.
That's exactly, and you know, you probably get away with just about anywhere else, except maybe the reading room, right? It's just, or you put it on its own little stand and just keep it off the building a little bit, but no, those indoor units are, you know, I mean, that was the goal, was to be very quiet. They use a super efficient, you know, motor in them. They don't have a whole lot of extra oomph, and they have filters in there, we can kind of show you that, but. No, you know, you generally don't get any complaints about the sound. It's a fairly quiet sound. So here's some of these floor. I mean, this is just, again, there's just fin coils inside of here and a fan. And, you know, each one of these models goes with a specific outdoor unit, but, you know, in a lot of ways, I'm going, yeah, why am I blowing warm air up from the ceiling down? 90% of these was all for air conditioning, right? So the whole industry kind of, you know, was always focused on air conditioning. So when are they gonna
Where that cold air will fall.
Yeah, yeah,
Down into the
yeah,
house.
yeah, exactly. And so when are we gonna get these on the most efficient units? I assume it's coming.
But they work, yeah, they work. I mean, Jim Powell and Beth Bertula installed one of those in their place in Juneau. And we stayed they have a little apartment, and they had one of those in the apartment. Linda and I stayed there, and it heated the place.
Yeah, yeah, oh yeah, you know, you don't get that
sturdier.
cold, you know, layer of air in the bottom, but.
It's not I don't think it's as nice as baseboard heating.
Right,
You know?
or even a coil that's blowing that warm air right down into floor,
Yeah,
where you live instead of
Yeah.
up there on the ceiling.
but it works.
So other options, you know, they make these little fan coils that can fit in the ceiling or whatever, and you can do a little bit of ducting then, so you can, you know, if you got bedrooms, you just need a little bit of heat in each bedroom, it may make sense to plumb in one of these, and then with a little bit of short ducting to hit some other rooms. So other ceiling options.
By the way, I see in the chat, it looks like someone has asked if you can get a copy of this presentation. The answer is ish. It's actually quite large. It was too big to email. But if you go ahead and contact me, we'll see if we can't work it out.
get it on a site somewhere. I stole all these pictures, so I have no. I'm claiming no ownership, so I'm more than happy to share this. If there is a way to get it on somebody's website, that'd be fine.
We will get a recording, right?
Yes, I'll be sending out the recap for sure,
Yeah.
Mike. In fact, as soon as this meeting is over, because I want to announce some more of the CCHRC festivities.
So just more options in terms of various, again, these are just, coils in there with some fans running that warm refrigerant to those deals and blowing warm air or cooler, depending on what your needs are at the time. There's some more air handler options. So maintenance, really the only thing a homeowner gets to do with their heat pump is clean the filter on the inside unit. Obviously, somebody was a little lacking here. And if the unit isn't getting that airflow, you're not getting the efficiency out of the unit. The heat pump, it's just like having super dirty coils on your refrigerator. All of a sudden you're just not cooling things down like you used to, and the poor compressor is working against all of this. And so for the homeowner, it's cleaning these indoor little screens. And every now and then on the outdoor, you got to clean the grills on the outdoor unit. That's it.
Is this a shop vac kind of thing?
Yeah, shop vac and a little bristle brush kind of deal. And, we're talking yesterday, in the wintertime, I haven't had to clean my coils in years because there's nothing really in the air in the winter. But if you're going to do a little air conditioning, use it in the summer. I mean, the cottonwoods, for example, are doing their things. Mosquito eaters are out in force. Yeah, you're gonna have to, every fall, it'd be nice to go give it a check and make sure you get it cleaned out.
On your system.
Yeah, and in the real world, just like you have a oil service tech guy come and, clean and tune your boiler for you. These refrigeration guys will do the same thing. They'll come with their little shop vac but yeah, clean your indoor one for sure. That's designed. So all the joys of where you put these outdoor units. They don't like being in snowbanks. They don't like being under waterfalls. And Seward, never had a problem in the last 5 years until this year. We had these huge snowfalls. And drip, your overhang drip thing, everything changed. And next thing you know, we got ice forming and stuff. And so it's really common sense, we gotta be blowing a lot of air through there. And if we're not moving the right amount of air, we're not getting the efficiency out of them. Here's one this winter. It was an older guy that just wasn't getting out much during this weather. And his whole unit just kind of frosted up on him. In fact, it fried the circuit board and had to replace the fan motor on it. Warranty issue, but it was kind of tough. And whereas that's been there for a number of years and never had a problem until this, we had this heavy snowfall. Here's kind of my unit. Of course, I got temperature sensors and things and monitoring stuff, and so it's protected under my overhang, but I couldn't get to it, so. Gotta keep that snow moved away. So this is my unit, and this cover on here, I checked one time and it was all completely frosted up. And I'm going, what the? And I go out there, I had a little drip coming down from the gutter, and it was running to the back, and it created one little icicle in the back of the grills there, but it covered up a temperature sensor that screwed up the defrost system. So I wasn't going into defrost, and I just kept clogging up. Well, so you get to put it in air conditioning mode for a while. So now all of a sudden it's pumping heat from your house to those coils. And so I gave it a super defrost basically and got that icicle off of there and said, all right, I need some kind of a cover. I'm protected from snow and stuff. I'm up high enough, but that drip got to me, so I just made a little cover just to make sure all that water drips to the outside. Same thing with my little mini split for the apartment. That clogged up. Yeah, a joint in the gutter, which normally wasn't a problem, except we had 4 feet of snow on top of everything and the snow was curled over the overhang and all of a sudden now we had, the drip problem. Yeah, again, that's Seward. So here's a picture of my, this is very typical, especially when it's warm and humid out. These are cold coils, just like that old refrigerator that you had where you had to clean the freezer, the frost out of the freezer. So these things are designed like every hour, they'll check their temperature sensors on their coils. What's the temperature coming in to the coils? What's the temperature going out? And they need to get a little smarter, but they know when to defrost. So they'll turn this thing into reverse and actually warm up those coils. And then all this water drips down. And there's a pan on the bottom there. A lot of the cold climate units will have a little heat tape down there to make sure we get that water out of that unit. Well, the critical part is when you see this water runs down to the ground, where's it gonna go? If you've got a driveway or a sidewalk right next to this thing, you got a glacier. So you just gotta think about, and if the stand isn't off the ground, you're just gonna form a big blob of ice underneath it and it's not gonna drain and it's gonna fill up with water on the inside and so you just gotta be thinking about it. That's where hanging these things high up on a wall is kind of nice where, you got plenty of space or put them on a stand where there's plenty of room for that water to build up a little bit and drain away. So it's interesting and it's just, building science when it's 20 below out or 0 out or 10 degrees out, there's not a whole lot of moisture in the air. So you really don't build up a lot of frost when it's really cold out. When you build up the frost is when it's like 30 degrees. Because you think about, if you think about heat transfer, to get heat out of that cold air, these coils, that refrigeration cycle has to make that refrigerant significantly colder than the outdoor air for it to be able to absorb heat from the outdoors. So even when it's 33 degrees out, these coils might still be 20 degrees, 25 degrees. And if it's really moist out, you're going to accumulate a lot of moisture. And that water's got to go somewhere. So up in Fairbanks, these pan heaters are essential. Seward, probably not so much because we don't really see, those kind of long periods of cold freezing temperatures. But yeah, so think about where that water is going to go. A lot of different stand options. Again, just got to get it out of the snow, keep it from water pouring on it, or at least on the backside. Yeah, so there's all these metal stand manufacturers. They actually make little covers for them. Just got to make sure we have the circulation of airflow going through there. I like this one. This goes up a little higher. This is in Juneau. Bob, he put in 2 of these units, one for his downstairs, one for his upstairs, and he decided to stack them. I like how he made a little slope roof there, so the water dripping off of the upper one isn't dripping on the bottom one kind of deal, and I thought that was pretty cool. These little roofs probably make the most sense, just to keep that water and stuff, give them a little protection. And how you do it, could be very simple like I did. I just put something, a little topper on the top. The only thing you got to remember is that circuit board for these things, the brains of these units, you access them from the top. So you have to have a system that you're going to be able to get at that very top. Now this one I got kind of some issues with. I don't think they're really getting the airflow through the back side of this unit, for this air to flow through there. So more questionable. This is kind of nice. I wish it was up a little higher away from the snow, but obviously this homeowner kind of understands he's got to keep the snow cleared. But had we put that on a higher stand, I thought that looked pretty nice. Just giving you some ideas of what, here's some sheet metal outfit that makes a little cover, again, a topper that just keeps everything from getting into the back. And some of these, they make them so they actually line up with the holes on the top of the cover and stuff. So just something to think about. This is my sister in Minneapolis. She's got 100-and-some-year-old house, and this was like 4 years ago, and this is probably kind of Fairbanks. I don't know how many HVAC companies there are in Minneapolis. We cannot find one that would install a mini split. They all wanted to put in central air conditioning, all right, the regular, their standard operation. Well, she just wanted some coolant during the worst of the summer in her main little living room area. And then this unit went upstairs into a bedroom. She didn't want to, it's an old inefficient house. You're going, no, I don't want to cool the whole house. I want my bedroom cooled off a little bit and stuff. So I had to come down and we had to, so my brother-in-law fortunately helped out and we put them in. And her neighbor, carpenter lady, did a really nice job on that little cover. So kind of a nice system. But again, the installers just wanted to, do it all. Just some more pictures I just kind of want to show you. We've been building these little all-weather wood stands, for a 4x4 and 3 or 4 2x4s, and because those metal stands, they want like $300 for those little metal stands. And with this, we can make them as high as we want. And so this was my other little research project. A gal that lives in an old log house, leak here in a sieve. I knew this heat pump wasn't going to be big enough, but boy, was I wrong on how not big enough it was. This poor thing, when it gets down to about 35 degrees, it's running full bore all winter long. And so there we are. Originally, there's drain holes underneath here for all that defrost to go down. So I just cut a 3-inch hole and lined it up with that drain hole, and that froze up. I blocked it up some more and I made a bigger hole. I made a funnel and that all froze up. Pretty soon I finally went down there with a Sawzall and cut a foot square chunk out of her deck just to get out of there, because there's an incredible amount of moisture when this thing is running at those milder moist temperatures full bore. But
So sizing, just sighting are very important.
right. And again, where's that water gonna go? They're gonna frost up. That's just physics. There's just no way of getting around the physics of them frosting up. So it's been kind of fun. She could have used a bigger unit. The goal was to get it weatherized. And maybe we'd reduct this one down into her basement and she'd put a bigger unit up front, but she got a really good deal on it, so I don't feel too bad. Here's some new construction kind of ideas. Again, you can see it a little higher, but you can see where you can kind of make a fairly clean installation. Always, compromises, somebody decided, here's a place to put it, but, we gotta clean those coils, service guy's gotta maybe get up there and work on it, so maybe that was his only choice, my big concern when I first put mine in, I didn't want to point it towards the neighbor's house. I was kind of afraid of the noise. But it turns out they're really not that noisy, from 10 feet away, it's, you can talk just fine. I mean, wasn't as big of a deal, but that compressor does make some vibration. And so when you put them on a stand like this, you will get some of that vibration sound through the wall. So where you mount these things is important. The one on my apartment, I gotta put my ear to the window, which is only 4 feet away from my unit to hear if it's running, so.
But in this instance, that white band underneath.
So that's where the refrigerant lines
Those
are
are the lines,
running,
okay.
right? Off to wherever they have the indoor unit is, right? And this is a disconnect box kind of for the service guy, so he can go and disconnect the power when he goes in there and mucking around with the electrical side of things. That's a code requirement. So yeah, so now it's a question of, we gotta get power to it. So if it's on the opposite side of the house, it'd be a breaker panel. It's kind of like, okay, there's ching ching, you know, for the electricians to run. So how close can we be to the source of, you know, power? And how close can we get this unit to the indoor unit? So you sort of got another compromise. I mean, it's all doable. You can run these refrigerant lines for hundreds of feet, I think. So it's not a distance issue. It's just economics and location, location, location. So this is still kind of, the big discussion is, do you put in one big unit? So this unit actually has two indoor heads. You see one running downstairs and one running upstairs. And they actually make these where you can do 3 or 4 heads. And it just becomes a question of, you know, what's the comfort level? Can they maintain temperatures in all these 4 different rooms with this big unit? And we'll get some milder temperatures, you know, and you don't have much of a load. This big unit's going to be cycling more versus, which is still kind of the energy geeks are saying you're really better off having 2 small units outside and running 2 separate, you know, indoor heads. Because then when it really does, the temperatures are mild enough, these things will ramp down way more than one big one. So efficiency wise, 2 separate units are still better than one big unit. Cost wise, these 2 separate units are a little bit more than one big unit, but you have some redundancy, you know, if you got 2 units and if one of them for whatever reason died, you still got getting heat out of the other one. So interesting debate. Maybe someday they'll make these big units as efficient as little units, and you know, that discussion will change. I saw this picture and going, here's somebody who did not want a big unit and a lot of heads. I think the installer was pretty happy with that. So where would I start with? You know, I'd recommend, let's just put in a mini split, you know, the 12K, sort of the most efficient unit we can, find a good location for it, and just, you know, run it, get used to it, understand, you know, what it can do and what it can't do. And that'll give you that little bit of air conditioning in the summer, especially when during your smoky seasons, we want to keep everything closed up. And then really, you know.
Actually, the second one's the first, which is make your
Right.
structure as energy efficient as possible.
Well,
By weatherizing.
you know, I've always said that. In this case, I'd go ahead and put in a heat pump.
Oh.
But don't oversize it. Put in a small one and just let it run. And that extra $4,000 that you save by not putting in a huge one and ducting it all over, let's put that into weatherizing your house. I think it bigger bang for your buck. You know, but yes, now, of course, weatherizing your house is good for everything. So, you know, and then once you get going, this heat pump, you know, going to air to water heat pump, I think the technology and the options are going to just keep improving. So, you know, you might be able to have the opportunity then to add another one. And you put in that air to water heat pump, now you're taking care of your domestic hot water. And you can supplement heat to the back rooms. So here's a Toyo, here's something RE sells, and other manufacturers make. Again, this is just a fan coil. There's just coils inside of here and a nice quiet blower. So we can run warm water from your air water heat pump tank to these units. So you can be putting those in back rooms. So just running some PEX tubing to this thing, going from your water heater and the little pump, we can actually get some heat into the back rooms. And now that you've weatherized it, you know, you don't need loads, and I think all of that can work fine.
Okay. Oh, perfect. That was gonna be my final question. Again, how This has been wonderful. This is wonderful, but if, with whom and how can someone follow up to have those more detailed discussions as they start to figure out, what kind of size, what kind of location, what product?
Right.
Okay, excellent. So if you don't mind. So Department of Energy has a heat pump page.
Yeah,
CCHRC.
so see, they've got a lot of good info on there. That NEEP site had a listing of all the different products and all their specifications and stuff. If you just go online and Google cold climate heat pumps,
It's a lot of info.
you'll be able to read forever and watch lots of YouTubes and stuff, and which product is better than another. I mean, is a Yamaha snow machine better than
Well, I noticed everybody pulled up in Chevys this morning. So I'm glad no Ford people showed up. All right. Well, hey, everybody. Again, we are past the top of the hour, nearing the bottom of the hour. But this has been a wonderful conversation. Thank you so much, sir. The conversation continues. Again, it is CCHRC is bringing us the Housing Action Week. So again, there's lots of festivities. You can go on their website and get the full breakdown of the schedule. There were things yesterday. There's a bunch of stuff today, all day. Tomorrow, a full symposium on Thursday. The list goes on and on. Are there any final questions or comments? Mr. Music?
Yeah, I'd like to bring your attention to the home show Friday, Saturday, and Sunday. And Phil will be teaching a class on heat pumps on Saturday afternoon.
So if you want to watch these slides again. Or actually ask some hard questions, now that you get the chance to think about it.
That's right.
You can hit me up hard.
All right. Well, everybody, thank you so much. Phil did send me this emailed it in a way that I could download it. So if anybody does want the slide deck, just go ahead and give me an email and I'll forward that along if that's okay, sir.
Yeah.
All right, very good. All right, well, everybody, thank you so much. As always, I will let you know, I actually, I don't know that I have anything scheduled for next week. But of course, when I do, I will let everyone know. Beyond that, again, just enjoy the rest of your Tuesday. Do participate in Housing Action Week all week. Hopefully we'll see you there. And just be well until we see you again for the next Energy for All Alaska Task Force.